Hello. In the previous lesson we briefly touched on the topic of compiler warnings as well as core coupling orientation. In this lesson we will discuss topological conflicts, which are important to fully understand the compiler warnings resulting from electrical model degenerations, as well as partitioning problems associated with placement, orientation, and parametrization of ideal transformer core couplings. So, what are topological conflicts? Topological conflicts are a set of modeling problems that arise due to a specific combination of elements within the ideal electrical circuit, which can cause unexpected or incorrect simulation results. Let's start with an overview of all the topological conflicts that could occur. There are two main types of topological conflicts: state degenerations and source degenerations. Let's dive into state degenerations. State degenerations are topological conflicts that occur when either the voltage source is connected in parallel with capacitor or the current source is connected in series with inductor. In the first case, the capacitor gets degenerated, meaning that the circuit behaves in exactly the same way as if there was no capacitor connected at all. The same occurs to the inductor in the second case. Let's see what will happen if some of these degenerations occur in our model. Now, let's add capacitor in parallel to the voltage source. When we compile this model, we receive a warning about a bad voltage loop which is detected and that capacitor is degenerated. Basically, this warning is informing us that the capacitor has no impact on the circuit. This error should be familiar if you remember the previous lesson, since it was discussed there as well. However, this warning is slightly different than the classical bad voltage loop warning, and should be dealt with differently. The reason why this is different is because regardless of the switch permutations, degeneration will still stay, even though the error message only mentions one particular switch arrangement where this occurs. Therefore, it is important that you can recognize these degenerations and know why the warning has occurred. You might already have sense about how to fix this issue. Simply altering the circuit by adding a snubber would fix this issue. Snubbers are elements that are used to increase the stability to the simulation. They are also an important part of model partitioning, and therefore we will look into them in much more detail in the next lessons that deal with model partitioning. In this case, snubber elements should be added in series to the voltage source or in parallel to the current source. Let's now talk about the next topological conflict type, source degenerations. There are two types of source degenerations: direct degeneration of independent sources and of independent sources with zero sources. We'll first explain the direct degeneration of independent sources. Degeneration of independent sources occurs when there are multiple voltage sources in parallel or multiple current sources in series. These degenerations won't cause an error during compilation but instead will stop the compilation process completely. Let's see this in our example. Let's add a voltage source in parallel with the already existing voltage source. When we compile, we receive an error that stops the compilation completely and therefore requires us to either remove the surplus of sources, or to include passive elements in between. Let's go to the second source degeneration. The second source degeneration is the direct degeneration of independent sources with zero source. In this case, zero sources are open and closed switches. These topological conflicts occur when there is a closed switch in parallel with a voltage source or when an open switch is in series with current sources. When this happens, the switches become degenerated, meaning that in the case where we have a switch and voltage source in parallel, the switch will always be open, no matter what control signal it receives. Additionally, any switch in series of a current source will always be closed, no matter the control signal. This means that having switches in parallel with voltage sources and switches in series of current sources has no effect on the circuit at all. Let's see how this impacts the compilation process. Let's add a switch in parallel to the voltage source in the model. Now, when we compile this model, we receive an error which warns us that the switch we added is degenerated. We have once again received a warning that points us to the specific converter arrangement. However, this type of degeneration is independent of the converter permutation, so you should fix the topology in general, not just for the particular case of this one switch permutation that the compiler warned us about. The compiler will not stop us from loading this model. However, it will simply ignore these switches during simulation. These issues can be fixed by adding snubbers, or more precisely by adding a snubber in series to the voltage source or in parallel to the current source. The topic of snubbers will be expanded in lesson model partitioning, where we address the problem of snubber parametrization inside the ideal transformer core couplings. In this lesson, we have covered every type of topological conflict. If you want to learn more about them, please refer to the documentation link in the materials section. Thank you for your attention.